The first rule of VSEPR theory says that the repulsion, the extent of repulsion are not the same for each of the pairs of electron pair. Okay, if you take two lone pairs, then the extent of repulsion is far more than the repulsion between a lone pair and a bond pair, and it is further greater than the repulsion between two bond pairs. So what is the first rule is saying? That they are repelling, whether it is two lone pair or two bond pair or one lone pair, one bond pair, each of them are repelling, but the extent of repulsion is not the same for each of the cases. It follows a particular order, that is lone pair, greater than lone pair, greater than bond pair, bond pair. So here I have taken the example of methane, ammonia and water. Okay. This is your methane, this one is ammonia, and the red one is the water. Now in methane molecule you can see for the central atom in its valence shell all the four are bond pairs, right? So when all are bond pairs, that means the extent of repulsion for each of the pairs is exactly equal. That is, the repulsion prevailing between these two bond pairs is equal to the repulsion prevailing between these two bond pairs. Similarly for these two, right? So all are in equal extent. That means all the repulsive forces are equally strong. And that's why the molecule possesses a perfect tetrahedron, and for a perfect tetrahedron the bond angle, that is the angle between two CH bond, that is 109 degree 28 minute, and it is experimentally observed also. Now when we come to ammonia, okay, this is your ammonia molecule. This one is the lone pair, and these three are the three NH bond pair. This black one is the nitrogen and these white three are hydrogen. Now as I said, lone pair bond pair repulsion is greater than bond pair. That means this lone pair bond pair repulsions, these are greater, these are stronger than this bond pair repulsions, right? So as a result, what happens, since this force is stronger than this force, this bond will bend like this. So what is the final result? If it was a perfect tetrahedron, this one was the angle, and now because of this stronger force of repulsion, this bonds bend. As a result, the bond angle decreases. So this greater lone pair bond pair repulsion leads to a decrease in the bond angle, and so this HNH, this bond angle decreases from 109 degree 28 minute to around 107 degree. Now when we take water molecule, then we know there are two lone pairs, right? This is your water molecule, two lone pairs are there and two bond pairs. Now lone pair repulsion is further greater than lone pair bond pair repulsion than bond pair repulsion. So because of presence of two lone pairs here, this bond will further bend and the bond angle will further decrease, and that's why in water molecule the bond angle that is experimentally obtained is around 104 degree. Okay, so from the first rule, applying the first rule, we can explain this experimental observation that when there is presence of lone pair in a molecule, in the central atom of the molecule, it leads to deviation in geometry. It tries to decrease the bond angle. Now the second rule says that if the central atom contains a vacant subshell in its valence shell, then the effect of the lone pair becomes more prominent. What is the effect of the lone pair? We have already seen in rule 1 that presence of lone pair try to decrease the bond angle. Now if the central atom in its valence shell, if it contains a vacant subshell, then this effect of lone pair becomes more prominent and it decreases the angle further, even more. So for example, we are taking two molecules, one is your ammonia and another is phosphine, PH3. So first we are taking ammonia NH3. So for this one we have one lone pair, and we have already seen because of greater lone pair bond pair repulsion, the bond angle HNH, it decreases from 109 degree 28 minute to 107 degree. So this can be explained in terms of the rule number 1. And here central atom nitrogen, its valence shell electronic configuration is 2s2 2p3. Fine. Now if we take the molecule phosphine PH3, analogous molecule, because phosphorus is just below nitrogen in the periodic table, and in both these cases the covalency is 3. So this is the structure, one lone pair. But what is experimentally observed, the bond angle HPH, it is around 94 degree. Too much of deviation. Why? Now see the rule. What is the electronic configuration of phosphorus? The valence shell, it is 3s2 3p3. But in the third shell, n equals to 3, there is one subshell, that is 3d, and there is no electron in the 3d, so 3d 0. So this is the valence subshell. This is the valence subshell present in the vacant subshell present in the valence shell of phosphorus. And because of that, the effect of this lone pair becomes much more prominent and decreases the angle further to 94 degree. Here I am giving you another pairs of compounds as example for this rule, that is water and hydrogen sulfide or dihydrogen sulfide. Okay, so here again for water, the central atom oxygen, the corresponding valence shell electronic configuration is 2s2 2p4. So there is no valence subshell in the valence there is no vacant subshell in the valence shell, and that's why the deviation is only due to this greater lone pair repulsion, and it is only about 5 degrees, so 104 degree. But when you come to dihydrogen sulfide, then what happens? The central sulfur atom, in its valence shell there is a vacant subshell, that is the 3d, and that's why the effect of this lone pair repulsion becomes much more prominent, and it decreases the angle further to 92 degree, around 92 degree. So I hope the rule 2 is clear, that if there is any vacant subshell in the valence shell of the central atom, the effect of lone pair becomes much more prominent and decreases the angle, deviates the angle by a huge value. Now the third rule is saying that greater the value of electronegativity of the terminal atom, smaller will be the bond angle. So if you continuously increase the electronegativity of the terminal atoms in a molecule, then the bond angle starts decreasing, right? So one example I am giving you, that is ammonia and nitrogen trifluoride. One is NH3, another is NF3. So in NH3 molecule, they have a similar bonding, similar structure, one lone pair, sp3 hybridized nitrogen tetrahedral. Okay. Now after that, here the electronegativity of nitrogen is greater than hydrogen. That means here the electronegativity of the terminal atom is less, and the bond angle deviates from 109 degree 28 minute to 107 degree, and that is just because greater repulsion between lone pair bond pair than bond pair, rule number 1. But when you comes to NF3, this F is the most electronegative atom in the periodic table, right? So you have increased the electronegativity of the terminal atom by a huge value from hydrogen to fluorine, and as a result what happens, the bond angle further decreases to 102 degree. Now you can understand this one by the model. If I show you the model, you can understand it very easily. Suppose this is your NH3 molecule, right, ammonia molecule, and the electronegativity of the terminal atom is very less. So when electronegativity of terminal atom is less than the central atom, that means the bonding pairs are tending to get shifted towards the central atom. That means instead of being at the middle of the nitrogen and hydrogen atom, the electrons are actually shifted towards the central atom here, because nitrogen is more electronegative. So the electron pairs are like here, right? But when it is NF3, the terminal atom has the greater electronegativity. That means now the electron pairs will tend to shift towards the terminal atom. That means now the electron pairs are nearer to fluorine and away from nitrogen. And here the case is exactly opposite. They are closer to nitrogen, away from hydrogen. So now if I show you these two molecules, this is your ammonia and this is suppose NF3. Okay, these two molecules. So for NF3, the pair of electron are closer to fluorine. So as a result, the distance between the electron pairs is greater. But when you come to ammonia, NH3, then what happens? The pairs of electrons are closer to nitrogen, so they are close to each other. So because of this electronegativity difference, in NF3, the bonding pair electrons are at more distance. In ammonia, they are at close distance. Now you know, electrostatic repulsive force, it is inversely proportional to the distance. So since in ammonia the pair of electrons are close to each other, the repulsion between the bond pair will be greater because they are closer to each other. Whereas in NF3, since they are away from the central atom, the distance is greater. That means the repulsive force is less. So in NF3, the repulsive force between two NF bond is less than the repulsive force between the bond pairs of two NH bond in ammonia. Now, why is this deviation? Because of greater repulsive force between lone pair bond pair than bond pair. But here the difference between lone pair bond pair and bond pair will be less, because bond pair are also highly repelling here as they are close to each other. But here the pair of electrons of two NF bond, they are away from each other. So this repulsive force is weaker. As a result, this lone pair bond pair repulsion is much stronger than the bond pair repulsion. So here this lone pair can easily deviate this angle further. But here, since the bond pair repulsion is also strong, this lone pair cannot deviate it to that extent, and that is also revealed in the experimental result. Here the lone pair can deviate only about 2.5 degree, whereas here the lone pair can deviate by almost 7 degrees, 7 to 7.5 degree. Okay, so it is when the electronegativity of terminal atoms are increasing, the electron pairs are tending to shift towards the terminal atom. As a result, their distance is increasing, the repulsive force is becoming weaker, so the lone pair can easily deviate the angle, and hence it is showing a greater deviation of bond angle. Now rule number 4 is saying that the repulsive force of interaction between two multiple bond is much more stronger than the repulsive force of interaction between two single bonds. You know, multiple bonds mean double bond, triple bond, like that. So the meaning of this rule is the repulsion between two triple bonds, it will be greater than the repulsion between two double bonds. That will be further greater between the repulsion between a single bond and a single bond. That means when we increase the bond multiplicity or bond order, what is that? For triple bond, the multiplicity is 3. How many bonds are there? Or order is 3. For double bond, the order is 2. For single bond, the order is 1 or multiplicity 1. So when we increase the multiplicity of a bond, then the repulsive force also increases, just because greater amount of electron density. In a double bond, there are 2 electron pairs, so the electron density is greater, and that's why it exerts a greater repulsive force of interaction. Now these things will be revealed in the experimental result when we compare PH3 and PF3. Okay, phosphine, PH3 and PF3. So initially from the structure it may look like that in both PH3 and PF3 all are single bonds. So how can I apply this rule where multiple bond is involved, right? Now here we will counter a new thing known as p pi d pi dative bond or p pi d pi coordinate bond. Now what is that? If you see the electronic configuration of phosphorus, the valence shell in PF3, it is 3s to 3p3, just below nitrogen, like 2s to 2p3. So 3s to 3p3, and in that valence shell you have a vacant subshell, that is 3d. Whereas if you take the electronic configuration of fluorine, then what happens? It is 2s to 2p5. So two of the 2p orbitals are containing pairs of electron and one containing the single electron. So when you are considering the sigma bond, single bond, it is the single electron of fluorine in the 2pz orbital, and suppose the 3pz orbital of phosphorus containing another single electron, they are undergoing axial overlap to give you this pf sigma bond. In this way, from another fluorine you will take the single electron in 2py, that will overlap with 3py, give you another single bond, and in the third fluorine you will take the single electron in the 2px orbital, that will overlap with 3px of phosphorus to give you the third pf sigma bond. So in this way these three sigma single bonds can be described, can be explained. Now what happens next, in one of the 2p orbital, this pair of electron that can be donated to a vacant 3d orbital of phosphorus. In this way this type of overlap can happen. As soon as the sigma bond, single bond is formed, this p and f atoms, they are so close to each other that the 2p orbital of fluorine containing a pair of electron can undergo parallel or lateral overlap with the vacant 3d orbital of phosphorus. And since it is parallel type overlap, so it is pi type of bond. But in this pi bond, single electrons are not coming from phosphorus and fluorine. It is a pair of electron coming from fluorine. So it is a coordinate type bond. But the type of interaction is pi type, parallel. So it is known as p pi d pi, p orbital, d orbital involved, and the type of interaction is pi type. The nature of the bond is dative or coordinate because a pair of electron is donated from one of the constituting atom and the other one is receiving. That means there is existing a p pi d pi dative pi bond. I am giving it dotted line. This is the p pi d pi dative pi bond. Now this pf dative pi bond, it can exist between this pair, it can exist between this pair, it can exist between this pair. Suppose you are taking a snapshot. At this moment you can see the dative pi bond is between this phosphorus and fluorine. In the next moment, if you take another snapshot, you will see this dative pi bond is here in between this phosphorus and fluorine, because all are equally probable. So what is the net structure? One p pi d pi dative pi bond is uniformly distributed between all these three pf pairs. So one pi bond, one p pi d pi dative pi bond distributed uniformly at three places. That means each of the pair will get 33% of that dative pi bond. This one dative pi bond is contributing at three places, so each will get 1/3 of it. So this red one is the sigma bond and 33% of a dative pi bond. So the net bond order is around 1.33. This is also 1.33 and this is also 1.33. And as the rule is saying that if the bond multiplicity increases, the repulsion between two multiple bonds, here the repulsion is between two bonds where the bond order is 1.33, but here this repulsion is between two single bond. Here p pi d pi bond is not possible because hydrogen, it has only one s1, it does not have any pair of electrons so that it can donate. So here they are purely single bond, but here they are multiple bond character. These bonds have multiple bond character. They are like a double bond. So it is known as double bond character or partial double bond. So I have shown you the bond order will go around 1.33. So clearly here the repulsion will be greater, and because of this greater repulsion, it shows you bond angle. It shows you bond angle FPF, that is the bond angle between two PF bonds. is around 98 degree. See, here it is 94 degree, here it is 98 degree. Why? Because of greater repulsion between two multiple bonds. So if you try to apply rule number 3 here, you will get just the opposite result, because here the electronegativity is greater. So we are expecting an angle which has less value than 94 degree. But since here this multiple bond character is there, so we are not going to apply rule number 3. It is important to consider the multiple bond character here to explain the experimental result. Okay. Now, as I promised in the last class that I will come up with the answer for the question that I put in the last video, in the last minute, that how do we know whether the lone pair will be placed at the equatorial position or at the axial position here, right? And there I said that the lone pair occupies, experimentally it is shown that the lone pair occupies the equatorial position but not the axial position. Now, from this discussion of VSEPR 3, you know that the molecule possesses that geometry where the net repulsive force is minimum. So if you just see this trigonal bipyramidal geometry, this one, okay, this is trigonal bipyramidal, this is the trigonal plane, and these two are the axial positions. Now if I place one lone pair at the axial position, then we have 3 lone pair bond pair repulsion at 90 degree and 1 lone pair bond pair repulsion at 180 degree. Okay, so if I am placing it at axial position, 3 lone pair bond pair repulsions are there at 90 degree and 1 lone pair bond pair repulsion is at 180 degree, right? And then there are bond pair repulsions, 3 bond pair repulsions at 90 degree, 3 bond pair repulsion at 90 degree. Which fluorine? The other axial one, this axial one, giving you 90 degree repulsion, right? Now if I place it at equatorial position, now if I place this lone pair at equatorial position like this, okay, so this angle is 120 degree. That means I have 2 bond pair repulsion at 120 degree. Sorry, 2 lone pair bond pair repulsion, 2 lone pair bond pair repulsion at 120 degree. That is the lone pair repelling with the 2 equatorial fluorine, and 2 lone pair bond pair repulsion at 90 degree. 2 lone pair bond pair repulsion at 90 degree. And then there are some bond pair repulsion, this one and this one. So 2 bond pair repulsion at 90 degree, and this fluorine will also give 2 bond pair repulsion at 90 degree. So 4 bond pair repulsion at 90 degree, right? Here the most important factor is this one. Lone pair repulsion is much greater than bond pair repulsion, right? So here we have 2 at 1, greater the angle, less is the repulsion. So at 90 degree here we have 2 lone pair repulsion, but here at 90 degree we have 3 lone pair repulsion. So clearly, as a net result, here the total repulsive force of interaction will be much greater, that will destabilize the molecule. But here net repulsive force is minimum, that means the molecule gets stabilized. And we know from VSEPR theory that the molecule occupies that geometry where this repulsive force is minimum. And that's why in trigonal bipyramidal geometry, whenever you find any lone pair of electron, they always try to occupy the equatorial position. These things will be further discussed with other molecules when we will be coming with a video having the heading Bend's rule. Okay, there is a rule, you can try to search for it, Bend's rule. We will come with a video taking Bend's rule only with various molecules to show these things. So thank you for watching the video, and again I am saying to all of you that if you find these lessons useful for you, then do like, comment, share and subscribe and help the channel growing. Thank you.